Okay, let us begin our seminar with a 6 minutes delay. Our today's speaker is Aliaksandr Hubin from University of Oslo, who is visiting our group now, and he'll make a presentation about his research based on applying of statistical and maybe even Bayesian methods in deep regression models. Good. I thought they were not deep. Oh, this would be better.
Okay. Let's begin our presentation. Thank you very much for the introduction and for the invitation. My name is Aliaksandr Hubin, and I'm a PhD student at the Department of Mathematics at the University of Oslo. Today I'm going to talk about the most recent piece of the research we conducted, entitled Deep Bayesian Regression Models. And this work was conducted in collaboration with Genetically from the Department of Mathematics at the University of Vienna, and Florian Frommelt from the University of Vienna and the Medical University of Vienna. So let's begin with the introduction. Regression models are addressed for inference and prediction in pretty much a lot of different applications. At the same time, these days, more and more sources of data are becoming available, introducing a variety of hypothetical explanatory variables to be considered. Hence, model selection of the optimal combinations of different explanatory variables becomes extremely important, as well as in particular becomes extremely important to perform a proper Bayesian model averaging of different combinations of the variables for both good inference and predictions. At the same time, it is often the case that the linear relations which are used in the classical statistics are not sufficient for well-quality inference and predictions. However, simultaneously, one has to avoid too deep non-linearities in order to not face overfitting. And then requoting Einstein, make things as simple as possible, but not simpler, which is a famous known quote, which is, however, in the original was like this. It can scarcely be denied that the supreme goal of all theory is to make the irreducible basic elements as simple and as few as possible without having to surrender to adequate representation of a single datum of experience, right? So in this work, we are introducing a class of deep Bayesian regression models and suggest different algorithmic approaches for fitting them in order to try targeting and resolving the issues mentioned in the introduction. Okay, and let's begin with the model that we have defined and what we call a deep Bayesian regression model. Assume that we have some observations yi's coming from the exponential family distribution f, which is parametric and perhaps depends on some mean parameter mu I and the variance of dispersion parameter phi. We have n observations. Then the mean parameters are modeled with respect to the predictor, consisting of p different features of j, which are different functions of the original explanatory variables, which all have their beta coefficients on the outer layer and have some parameters on the inner layers that we're going to talk about slightly later. We also allow for r different Gaussian latent variables to allow modeling spatial temporal relations between the n observations that we have. Additionally, what is a bit non-standard is that we are introducing the latent binary indicators, gamma j's, which are in the domain of 0 and 1, which are switching on and off different features and latent Gaussian variables here, right? And all of the latent Gaussian variables are simply some jointly multivariately normally distributed random variables with the zero mean vector expectations and some covariance metric structure corresponding to different sorts of popular spatial temporal models like autoregressive process of order 1, autoregressive process of order p, moving averages, processes of different orders, random walks, so on and so forth. And these gamma indicators, in turn, allow us to select the optimal combinations of the features and the latent Gaussian variables.
Wait. I is an index of what?
So
is
I
an index of dimensionality?
No, I is the index of the observations, so we have n observations.
Okay, then why don't you have xi?
Well, because jointly we would like these features to depend jointly on all of the axes in order to allow some shifts, like lags, in terms of time for the axis. In most of the cases, they will only depend on xi. But some features, like lag, depends jointly on the whole matrix of axes. Sorry for that. Okay. If you have any questions or comments right now, it's a very important point to ask them, because here, I mean, the combination of the gamma vectors, like the joint vector which consists of the gamma j components, is something that we call a model. So those are described in different configurations of the models.
So gamma j shows what latent random factors are switched on and which one are switched off, right?
Not only the latent Gaussian variables, but also the features. Which features are on and off, and which latent Gaussian variables are on and off.
But j varies from p+1 till r plus p, right? Not from 1.
No, it was supposed to be from 1.
So it was
That's
from 1.
a typo, yeah.
And h is some simple function.
It's a link function. You know the generalized linear models? We need a link function to model the relations between the linear predictor and the mean parameter, like the
So
logic transformation for the success probability.
No deep networks here.
Not yet.
Okay.
They are coming via the features in the next slide.
And by the way, is age differential?
Yes, necessarily. The proper link functions, or the canonical link functions, are always differential. Okay, now we're going to describe the hierarchy of the features. With no loss of generality, we have said that we have at most p different features. And again, with no loss of generality, consider that all of the features are ordered with respect to their complexity. And then a new feature of j, or some feature of j with index j, can be constructed hierarchically and recursively via the previously defined features of k, or all of the previously defined features. In particular, we distinguish between 3 different possibilities to create a new feature. A modification, where we select some nonlinear transformation from the class of the allowed nonlinear transformations, B, and then just modify a feature with this transformation. A crossover, where we select 2 parental features with lower indexes, k and l, and then make a product of them to create a new feature. And finally, a projection, where we select all of the previously defined features as a vector of x, then make a semi-affine transformation of that, meaning that we have first a linear combination, alpha transposed of x, and then make a nonlinear modification of this feature. And as you can see, this, in fact, is very similar to what is done in deep learning, right? To apply the activation function to some set of features and modify it, right?
So why not just to take a neural network here?
The next slide is going to describe why. And interestingly here, alpha transposed is a sparse vector. There is a lot of zeros in it, and those 0 elements correspond to the fact that some of the previously defined features are not going to be influencing the new features. In the ultimate case, all of the alpha components are non-zero. But we're going to talk about this a bit later when we're describing the algorithm. Right? Now, we're coming to the motivation of why not simply apply neural networks. By the way, in the previous slide, it is a bit important that, of course, a modification and a crossover are particular projection. So you can find, like if we have just one feature and alpha equals 1, then we get a modification. And then a combination of the logarithm and exponent allows you to define a crossover via this projection operation. Okay. Why we have defined this hierarchy of functions, and what is it used for? We have defined this hierarchy of functions in order to be able to search through a very flexible class of different models. In particular, if you simply define the sigmoid hyperbolic tangents, a ref or a loop, as your non-linearities, then you can incorporate different architectures of the artificial neural networks by means of the features that we have. If we simply have the combination of the exponent and logarithm as 2 functions in our set G, then we, in principle, have all of the polynomials in the model space. Logics, easily incorporated in the model space. The AND for the two binaries is just the product. The OR for the two binaries is the sum minus the product. Classification and regression trees. And then this simple identity function, having x being greater than 1, allows you to branch different covariates and features in different classification and regression trees contexts. Seasonalities and Fourier series will be modeled by the sinus and cosine. Fractional polynomials, important for physics and other sorts of applications, simply adds the corresponding fractional polynomials degrees into the model. Again, recurrent structures. We can define lag operators which would shift your axis automatically and find the optimal recurrent structure if that is required. Okay, and then by the universal approximation theorem by Hornig, 1991, we are actually satisfying the universal approximation theorem once we have at least one function which is monotonous and bounded. For example, having at least one logit function in the set of non-linearities would allow you to, in principle, satisfy the universal approximation theorem criteria.
Excuse me, what does the star symbol mean?
Here, it's just the product,
What product?
multiplication.
But F is a vector, right?
Now, here, this is Fk and Fl. These are just two features.
Ah, okay.
And could you please tell more about this universal approximation theorem by Hornig?
So it just says that once you have a neural network with at least one hidden layer, and the activation function which is monotonous and bounded, then in principle you can approximate any function of interest in the domain of R.
And if the activation function is not monotonic, then it is not.
They have to be monotonous and bounded. In particular, ReLU does not satisfy this constraint. So
That was the
ReLU
reason I was asking.
does not allow you to approximate any function of interest.
I heard that there is some version of the theorem that extends to non-bounded functions.
This I don't know, frankly speaking. So I'm just referring to Hornig and the more original theorem by Chibenko from 1989, who has first proven that for the sigmoid, and then Hornig has generalized the idea for the monotonous and bounded. It might be the case that there are the more general versions.
It's enough actually just to represent indicator function. If you are able to represent indicator, you get the universal approximation. So by two rules, it's easy to represent indicator function, and that's why it works also for you, which is non-bound.
Times ReLU. Minus ReLU times ReLU with corresponding shifts.
Okay. Okay. Yeah. Okay. Agreed. I was interested why it's important to be bounded or to be monotonous.
But the monotonous means strictly monotonous or not necessarily strictly? Say if you have like a step function.
No, I guess it also has to be strictly monotonous.
Otherwise, you can use a constant, which will not work.
Right. Good. So we're done with the theory.
Yeah, anyways, yeah, right. But apart from that, of course, we have all the polynomials, and we have we can use simple Newton approximations, or like Fourier series approximations, which would in principle also approximate some functions of interest within the defined model space together with the universal approximation theorem by Hornig. Okay, we have done the description of the features and the motivation of why we have selected some particular nonlinear functions in the model space. But now let us go to defining the model priors, because we are trying to be proper Bayesian in our modeling and our math.
Something like.
And now we are going to talk about the model priors. The priors for those gamma indicators that we have talked about, that switch on and off different features and latent Gaussian variables.
And are these the only priors?
No, of course not. We will have also the prior priors. But let's begin with the model priors. So the model priors are defined in a way to penalize more complex features and more complex Gaussian random variables exponentially harder comparing to the less complex ones. And this is done via the following idea. So first of all, we are introducing two constraints on the number of features. So we are not allowing more than Q features per model. We also are not allowing more than R simultaneously, more than R Gaussian latent variables per model. Okay. And once we are satisfying this constraint, then we have a non-zero prior, and then we have some penalties for the active and non-active features. So the penalties for the features is of the following form. It's a product of the penalties for the individual features. Okay, and those individual penalties are parameterized as follows. So we have A, which belongs to the domain from 0 to 1. We take this power of gamma j times wj times cf f of j of x, where gamma j's are zeros and ones. If a feature is switched off, if it's 0, then this term becomes simply 1, and we do not get any penalization for that feature. Otherwise, if the gamma j is equal to 1, then we add some penalty, which would depend on the weight for the penalty, wj, which is in current implementation is either 2 or log n, which corresponds to correspondingly the Akaike or Schwarz criteria, and the complexity measure for the feature, CFWJ, where currently at least, well, it just has to be some non-decreasing measure of complexity of a feature. But what we have defined currently, heuristically, absolutely heuristically, without any proper mass, is to define the complexity to be the number of all pluses, multiplications, and non-linearities within a feature. Okay? This is the total.
One question. WG, are they the same weights which used during the definition of the definition of the model?
No, there we use betas.
Betas.
These are completely different. These are just WHAs. Very similarly, we have penalization for the latent Gaussian variables. Again, we have some beta hyperparameter. Again, if latent Gaussian variable is on, then it's been penalized. Here, the omega k's are the corresponding weights, and the c of delta k are the measures complexities of the latent Gaussian variable. And again, currently, heuristically, we have defined them to be the total number of hyperparameters of the covariance matrices of the corresponding latent Gaussian variables. So that, for example, an autoregressive process of order 1 will have two hyperparameters, the covariance and the variance term. And the, for example, random walk of order 1 will just have one hyperparameter because we have the covariance and then the variance, and then we have one term of the diagonal, right? The more complex random variables, like autoregressive processes of order p, would have p plus 1, for example, or whatever hyperparameters. And of course, we would like to have those covariance matrices of the latent Gaussian variables as sparse as possible. Okay. These were not the only parameters of the models that we are addressing. Of course, one has to define the priors for all of the other parameters. Conditionally on gamma, we are defining some multivariate priors for the beta coefficients, which depends upon the applications. For some applications, we simply use simple Jeffreys priors. For other applications, we use multivariate normal prior. But we will talk about that in more details during the description of particular applications of the approach. We also have to define some priors for the hyperparameters of the covariance matrices of the latent Gaussian variables. And finally, we have to define some priors for the dispersion parameter of the model. Right? We will talk about particular choices for the applications of interest. But generally, let's try to define the goals for the inference based on our model. So we have now said that we define gamma vectors to be associated with the definition of the model. All combinations of features of latent Gaussian variables correspond to all particular models. And thus, those vectors define all of the models. Parameters of a given model, which consist of the beta coefficients, the hyperparameters of the corresponding covariance matrices, and the dispersion parameter, is going to be defined as simply theta gamma. And hence, our goals are as simple as possible. We would like to get the posterior distribution of parameters and models, the joint posterior distribution. We would like marginal posterior probabilities of the models themselves. Finally, we would like to get the marginal posterior probabilities of some quantities of interest delta, which can be, for example, predictions. Right? For some reason, Okay, which seems to work now. However, we have challenges. So, given the number of features and latent variables q, we have 2 to the q different models to be considered, where q itself is simply huge. In fact, q itself is exponential in the number of input x's. And then we can't even specify the whole model space in advance because we won't have any memory of any computer to save all of the models for reasonably large problems. Now I'm going to describe the approaches we're trying to use to resolve the issues reasonably well. All of the approaches that I'm going to talk about are based on the marginal likelihoods. Okay? The marginal likelihood is simply the likelihood function where we integrate out the parameters from it. Right? So we have to integrate out all of the betas parameters, the hyperparameters of the covariance matrices, and dispersion parameter from the model to get the marginal likelihood. Of
and
course,
this is also known as evidence. Remember
the model evidence, I guess, from
Bayesian methods.
Yeah, the model evidence is the second name for this. This is often used as a model selection criteria, but we use it for different purposes. The problem and the thing to integrate out the parameters is extremely hard. I mean, tractable results where the analytical integration is possible only include the Gaussian models with the conjugate priors, and that's it. Otherwise, you have to use some approximations. You can use different sorts of approximations, starting from Laplace approximations, integrated nested Laplace approximations, the Gibbs sampling-based CHIPS method, the Metropolis-Hasten-based CHIPS-Gileskov methods, and many others. But the main computational constraint currently is that you have to use the whole sample of your data to approximate these marginal likelihoods. There are no methods feasible or available so far which would use subsampling techniques, which would allow you to compute the marginal likelihoods efficiently.
That's the stochastic relational inference.
At least of those that I know.
At least what?
Of those that I know.
Okay, but this is actually what we're developing right now. So there are some scalable methods which are based both on variation approximations, on scalable variation approximations using stochastic relational inference, and both for MCMC sampling.
Okay.
Stochastic MCMC sampling.
Do you want to say that for some small data sets this actually can work?
Yeah.
Well, actually, it's extremely interesting what you're going to do with gamma. This is not the major bottleneck in computation, this integral.
Well, in fact, it is the bottleneck that slows down the computations in a major fashion. So that I mean, if the dimension of the data is large enough, then the computation of the marginal likelihood can simply take forever. At least using these methods.
Using these methods, of course. But well, anyway, this question, proceed.
So, but consider now that we have the methods for computing marginal likelihoods available, whatever these methods are, and then let us see what we're going to use the marginal likelihoods for. So, first notice that the joint posterior probability distribution of models and parameters with respect to Bayes formula can be rewritten as a product of the conditional posterior of the parameters of a given model and the marginal posterior of the model. Right? We have just said that the marginal likelihood can be obtained by, for example, Laplace approximations. Similarly, that the marginal posterior distribution of the models by means of Bayes formula can be simply approximated as this. The main problem here is that in order to approximate the marginal posterior probability of the model, you have to integrate, or you have to iterate through the whole model space, which is infeasible.
Exponential.
It is exponential in the number of features, and the number of features is exponential in the number of x's. So it's extremely hard to do that. And of course, it's infeasible. But we are going to create the biased approximations, which are going to be only asymptotically unbiased, based on some subspace of the model space, which we call the renormalized estimates of the posterior probabilities. And the motivation and the idea of building them is built upon the following logic. So if we do not visit the models with zero products of the marginal likelihood and the prior, which do not give any significant contribution to the denominator of the Bayes formula, then we're not inducing any significant bias. And those models themselves have a zero posterior. However, if we miss some of the important models with high values of the marginal likelihood and the prior, which gives significant contribution to the denominator, we are creating significant bias. And we would like to visit as little models as possible and simultaneously have as large mass in the denominator of the bias formula as possible. And this builds the motivation of what we want to achieve and which algorithms we are going to build. And in the case of the model spaces, where the model space omega gamma can be pre-specified in advance, and you can enumerate all of your features at least. This was feasible by the mode jump in MCMC algorithm that we have developed a few years ago. And this algorithm is based upon the following idea. So this is an adaptation of the Monte Carlo, where we have a mixture of different proposals. And with a high probability, we have a local proposal which explores the space of solutions around the given mode, right? But in order to get away from the local extrema, with a lower probability, we have the following proposal, which consists of 3 steps. So we then generate a large jump in a new part of the model space, which is extremely likely not to hit the mode. And if we were to accept or reject this solution with respect to Metropolis-Haston acceptance ratio right away, we would most likely always reject, right? But instead of rejecting or accepting it right away, we suggest making some local, in our case, combinatorial optimization to get to the local node by means of some simulated annealing procedure or local greedy search or taboo search whatsoever, your favorite combinatorial optimizer, to get to the local node. Then randomize irreducibly around that mode. Okay, and in order to calculate the acceptance ratio, we have to make a symmetrical backwards or reversible jump, make optimization and calculate the transition probability to the initial solution. We have shown that this is going to be ending up with an irreducible and ergodic procedure having the right target distribution, but this only works for the cases when the model space can be specified in advance. For example, for the linear models. This is not the case for the deep non-linear regressions, which we are addressing. And hence we have suggested, yeah?
Please, one question. What is irreducible in this context?
So in a way that, in this context, it means that asymptotically, in order to get the ergodic Markov chain, it has to be at least reversible and irreducible. So it has to be able to visit all of the solutions.
This is the meaning of
Irreducibility, right?
Okay.
For example, having this simply Bernoulli probability of changes of all of the components with a very small probability of changes here will work as an irreducible kernel at this point. Okay. Genetically modified and MCMC idea, which we have developed in order to be able to deal with these complex, deep Bayesian regression models. The idea is very simple. The MCMC algorithm is embedded in a Markov chain of the different sets of features which allow us to explore different parts of the model space by means of the MCMC algorithm. And those sets of features are a fixed and well-defined size D. And then each of those sets of features induces a separate search space for MCMC to explore. And then in the language of genetic algorithm, we call those S's as populations. Then those populations of different features dynamically evolve as a Markov chain of populations through some states, to allow the MCMC explore different reasonable parts of the totally infeasible large search space. Right? Each new population is selected from some neighborhoods of the previous population, where the neighborhoods is defined by several operations, like mutations, crossovers, reductions, modifications, projections, and filtrations. We're going to describe those in detail in the next slides, which are applied to some current population as T and a special set F, which we're going to describe in the next slide as well.
How do you choose number of features?
This is a very good question. This depends upon your computational possibilities of your computer, how many cores you can use simultaneously. This depends upon your constraints Q and R that you have defined for the number of features and the number of latent Gaussian variables. We can only achieve irreducibility in the global search space, so that asymptotically we will visit all of the possible models, if D is at least larger or equal than Q capital plus R capital that we have defined as constraints on the total number of allowed features and random effects per model. Yeah, that's the main motivation. Another important quantity is defined via formula 10, where we define the posterior importance of a given feature based on some set of models V, which simply is the marginal posterior probability of a given feature to be equal to 1. And this allows you to evaluate the importance of a feature on the set V. Those probabilities are going to dynamically evolve as we add more and more models in set V, but we're going to very actively utilize those in the algorithm to allow generating good proposals. Again, the pipeline, to make sure that we understand what we are doing, we begin with the S0, which is a set of all P input explanatory variables. Then we construct the first population by means of running MCMC for some number of steps on this initial population. We select the best members from this population via a filtration operator. The rest members have been filtered out in a special set F and are being replaced with D minus D1 new members, which are generated by crossovers, mutations, modifications, projections, and reductions. The same applies for all of the other populations. So we again run MCMC on a model space which is induced by ST features for n steps. Select the best members of a current population which survive for the next populations. Others are being filtered out and deleted forever for other steps. And the remaining D minus D1 members are being filled in by means of crossovers, mutations, modifications, projections, and reductions applied to the members of the previous population and this special set F, where we have filtered out all the not important features from the initial, yeah.
Are you looking here for only one optimum? Because
No.
For instance, in genetic algorithms as well, there is a possibility that you, for instance, find an optimum, but remembering all the, well, in particles from transition, for instance, it's not genetic, but still, you can look and find other optimums, because it's a global
Optimization procedure. Here we're not interested in finding an optimal at all. We are interested in searching through the model space and finding posterior probabilities of all of the models that we have searched through. So the motivation is to build this set V of the models, which is a subset of the total model space, which is going to be used for approximation of the posteriors of interest and performing Bayesian model averaging.
Is it true that during this procedure you don't use any gradient information?
But in fact, we don't have any gradient information because we are using this.
When you're sampling parameters, like theta.
We are not sampling parameters theta because we are using Laplace approximations to integrate them out, so that we are working in the marginal space of only configurations. Okay.
Does it have something similar, something common with the particle swarm optimization technique? It seems that this is pretty much the same. We have a number of particles, and each particle is trying to locate its own mode.
Might be the case, but I haven't been looking in detail into the relations with them.
Well, does actually Laplace approximation works when you have two layers of?
It is much harder to perform Laplace approximations for the two layers, but that is why we define the models the way we have defined them. So we use Laplace approximations only for the outer layer. So they only depend on the beta parameters, right? All of the other parameters for the inner layers are considered to be used in the feature engineering procedure. So they're not becoming the parameters of the model, so we are not using triads for those. And this is somewhat a disadvantage of the current approach, which gives some limitations, but that was important to make this assumption to be able to have feasible computations.
So do you optimize them during some procedure afterwards? Or?
Okay, I think we need to talk about this in more detail. So once we have suggested a projection, and say that we have selected a projection of the form fj to be equal to some, let's say, sigmoid f alpha 1 f fk plus alpha 2 f let's say I, with no loss of generality, where j is greater than k and I, right? And then the way we are obtaining those weights currently is via a very greedy optimization. So what we are doing is we are simply making the alpha vector hat to be the argmax of the argmax of the product of the the product of the likelihoods of data given alpha vector and the prior for this alpha vector
For any given gamma.
for any given gamma. Right. So we make this greedy procedure to get the corresponding estimates for the alpha, which are kept forever fixed. And then we're optimizing only the alphas for the new layers, when the new layers are generated. Again, this is made mainly to make the computations feasible, because otherwise we won't be able to...
It's like greedy layer stacking.
Yes, in some sense. And this is a disadvantage of the current approach, but this is a limitation that we have to perform in order to be both able to use Laplace approximations of the marginal likelihoods and to make the search through the different configurations of the architecture feasible. In future, of course, I would like to get rid of this assumption. Okay. Yes?
One more question about the previous slide. So, am I right that S is a set of indexes for gamma?
Yes.
And MCMC outputs the set of values for those indexes, right?
It outputs, in particular, posterior marginal probabilities for all of the individual components of these S's.
So it outputs for a set of features or for a set of values for each?
Marginally for each gammas,
Yeah.
and gammas are just the binaries.
Yeah.
Right. And now we're going to talk in the next slide the very idea of why we're doing that. So consider the first step, where we begin with the linear models, and we search for the P0 linear explanatory variables. Right? Then we are approximating the marginal inclusion probabilities for the corresponding gammas, right? And for the gammas which are above the particular threshold, we are going to keep those in the new population. Others have been filtered out in this special set app, which we need for irreducibility of the algorithm at the end of the day. For any of the other search space, we are again searching through the current through the current population. Then we approximate the marginal inclusion probabilities of gamma i's to be equal to 1 for all of the members of the current S. Those that are above a defined threshold survive into the new search space. Others have been filtered out and deleted forever. Okay, and this is what we call the filtration operation. We have a crossover operation, which is based upon selecting two parents of I and of j and making a new feature as a product of those. As simple as this. And then fi and fj's are selected from a probability distributions where the individual probabilities are proportional to the current approximations of the marginal inclusion probabilities of the gamma i's to be equal to 1. Which means that we are more likely to select those features as parents which are have higher importance comparing to all of the other features. However, we have a non-zero probability of selecting any of the other features, including those that have been initially filtered out. Right? Because we just defining a minimum threshold for the selection probability to be non-zero. then most likely we're going to choose good features as the parents. With lower probabilities, we're going to select some less important features as the members for the crossover. The mutations. The mutations are needed to achieve irreducibility in the total model space, and this means that we are replacing some of the features that have been filtered out by means of the initial axes that have been, after the first step, filtered out in the special set F, that allows those features to come back to the model space and start building new features based on them. Right? This is important in order to be able to achieve irreducibility. Okay, the modification operator. Okay, here we define in advance the discrete probability distribution for different non-linearities. We draw from this distribution to select the non-linearity. Then we select the feature, again proportionate to the current approximations of the marginal closure probabilities, and simply modify this feature with non-linearity, with no coefficient at all. Finally, the most complex operation is the semi-affine projection operator, where we select some set of features which exist previously, make a linear combination of them, estimate alphas, which are fixed forever after this, and then perform a non-linear modification of that.
You mean A and B by alphas?
Yes. In this case, it's A and B. And this is a very toy example, which is most simple to illustrate how this step works. Okay, the reductions, or the pruning operator, which allows you to prune the features. Again, if you have a feature which becomes larger than the maximum feature size, which we can define by a constraint of C, having that the feature that won't have more than, for example, K or C complications, then we select this feature, and then with independent Bernoulli probabilities PD, we delete different components, like sinuses or multiplications, and then we stick the feature together with the multiplication. Yeah, right?
Yeah. So just to be clear,
Yeah.
when you choose features, you first filter them, then
Yes.
you mutate them, and then you modify them in the ways that you have shown, right? And
Not
then you repeat the procedure.
Not nearly as that, but not completely. So we are first filtering the features that are not important. Then we can either make crossovers from the features that have survived an initial set of F's features, or independently we can make mutations, or independently we can make the projections.
Okay, and how do you choose? So there is some
Probability distribution for the choice of whether we make a projection. Yeah, a very good question that I haven't talked about in detail. That's correct. So finally, then we prune this feature, coming back to this problem, right? And out of a more complex feature, make a pruned feature, for example, like this in this toy example, right? Apart from that, the genetically modified algorithm is not at all an MCMC at all. So just a genetically modified MCMC algorithm where we have a genetic modification of the Monte Carlo. It is not reversible, and it does not have the target distribution which corresponds to the posterior distribution of the models. However, we can make a small tweak by means of making a reversible MCMC algorithm, which relies upon the very same small jumping idea. Here, by the large jump, we simply understand the switch of the populations. And then by optimization, we understand searching through this new search space induced by the new population. And then the only thing that we have to do is to randomize the reducibility at the end of this search in the new population, and then calculate the acceptance probability of whether we're going to get to the mode in the new population, or we're going to remain in the mode in the previous population. And if we do so, then we continue searching the previous population. Otherwise, we start searching through the new population, and then by this step, we allow making transitions back in terms of the populations. I have some we had irreducibility previously. Have some reversibility, and this is going to then converge to the true posterior, and the frequencies of the particular models have stayed in the particular models, would also converge to the marginal probabilities of the corresponding models. So we have two different ways to approximate posterior probabilities of the models. One, which is a biased approximator based on the Bayes formula, which is going to only be asymptotically unbiased when we explore the whole model space, or the unbiased approximations based on the frequencies of the Markov chain, of the ergodic Markov chain, abstain in the corresponding models. Right? Because the target distribution corresponds to the marginal model probabilities.
That's right, but how can you guarantee that you sample from unbiased distribution using this MCMC?
Well, once it has reached the ergodic regime, then we are doing so.
But you need to check the detailed balance?
Yeah, of course, and this is satisfied with these transitions.
Uh-huh. Because of what?
Because there are these auxiliary states, Markov chain, Markov topology. So we extend the space of states by not only having those marginals as the models, but we have this total, the total proposal, or we are drawing from the joint probability distribution of gamma, gamma 1 to gamma k, which is the optimization, and the proposal gamma star. And in this joint model space, we are able to guarantee the detailed balance. And then our distribution of interest is only a marginal in that case. And this is some theorems that have been initially proven by my supervisor like 5 or 6 years ago in the journal of computation, in the journal of in the Scandinavian Journal of Statistics. So we're just referring to that theorem.
So in some sense you're using auxiliary variables?
Yes, exactly. These are exactly the auxiliary variables.
What is pi?
Excuse me?
What is pi in equation 15?
Pi is the product of the marginal likelihood and the prior.
Mm-hmm.
And this is just the randomization kernel at the end of the procedure. And that is sufficient.
Mm-hmm. Mm-hmm. Okay, seems more or less fair.
Okay. Now a very important step. The algorithm can be embarrassingly parallelized in the following fashion. We can simply run B chains of genetically modified MCMC algorithm or the reversible genetically modified MCMC algorithm in parallel on different CPUs or nodes, whatever we have available. I don't have the GPU implementations at all, so currently I can use all the CPUs. Then we combine all of the unique models visited by all of the independent chains into the set V. Then we can use the Bayes formula 9 to compute the posterior marginal model probabilities. We can compute the marginal inclusion probabilities that we have talked about of individual gammas to be equal to 1. Again, based on this set V, which we have embarrassingly parallelly explored. And finally, any posteriors of interest can be obtained for Bayesian model averaging based on the Bayes formula. So say that we want to have predictions, distribution for delta. Then we are iterating through all of the models, get the individual predictions for the models, and then the marginal probability of the model. And we simply integrate now the models. We get the marginal predictions based only on the data, which do not depend on any combinations of the models at all. And this we call Bayesian model average. Okay. Finally, we are done with the algorithm, and I will try by some simulation examples and some real data example to convince that in some application this can be not the most stupid thing to do. So for the experiment design, we have addressed several different examples. The first example is very simple. We have generated 100 independent data sets with 1,000 observations in each, and in each 50 independent binary covariates, where the x's are binary. The covariates were then assumed to be independent and Bernoulli with the success probability 0.5. And then the y's were drawn from the Gaussian distribution with the error variance equal to 1, and the individual expectations of the following form, which could have some, this is the data generating model, so we have some predictor, or the mean, which depends on some features linearly, some two-way interactions of some features, some three-way interactions of some features, and some four-way interactions of some features, which, again, even at this layer, induces quite some combinatorial complexity of recovering the features, because even for the two-way interactions, we will have n times p minus 1 divided by 2 features, and then this is going to explore explode even further with 3- and 4-way interactions. A toy example. We only address the product here because we want to compare to the previously developed logic regression, not to be confused with the logistic regression, where by the logic regression we understand the regression where all x is arbitrary and then we are recovering logical expressions in some normal forms, for example, right? And then we have addressed the following Gaussian deep regression model for this example. Here we are going to specify, by the way, the particular choices for the priors, right? So we have the Gaussian independent observations with the mean parameter mu I and the variance parameter sigma squared. We don't have any latent Gaussian variables in this example. All of the observations are independent though. We have the predictor, right? Then we have the following form of the prior for the model, so we don't have any constraint for the number of the covariates here, and also any constraints for the corresponding latent Gaussian variable because we don't have any. And we have here the log n penalty, which corresponds to the Schwarz type penalty. This is used because this is an inference-based example. We are not going to make predictions here. We are going to recover the true features and to see whether we can recover the true features here. The true logical expressions, if you want.
But doesn't it contradict to the desire of making predictions?
No, but we're not making predictions here. We want to recover the features of importance.
But we can also make predictions.
Yes, we can, but not for this example. Here we are interested in recovering the ground truths.
Okay, I got it.
So, and for those problems, at least for the linear models, Schwarz has proven the information criterion to be asymptotically consistent. So if there is a true model among the set of linear models that we are addressing, then asymptotically the IC is going to capture that with probability 1. Okay. Anyways, here we're using the simple Jeffreys prior for the beta parameters, where Jn is the Hessian information matrix, estimated at the maximum likelihood, estimated betas. It is an improper prior, as well as we have an improper prior for the dispersion parameter. And this is important to use the Jeffreys prior because it cancels out with one of the terms of the Laplace approximations. Computationally, this is a bit of a, in a way...
so you perform some kind of reverse engineering?
Yeah.
How to establish prior in such a way so that it could...
Exactly. It might be said as not a very fair thing to do, but computationally it is very easy to do that. And then the non-linearities that we allow in this example were cosinus, sigmoid, hyperbolic tangents, the tangent, sinus, and x absolute value to the power of 1/3. And exactly this model is going to be used for the 3 first examples that I'm going to talk about. Not only for this simulation study, but the 2 other examples to follow. Exactly the same definition of the deep Gaussian Bayesian regression model. Then we have performed the GLMM and RGLMM on all of those 100 generated data sets in order to be able to estimate the power and the false discovery rates of recovering the features. In particular, the linear features were recovered 100% of the time, and by recovery we understand that the posterior marginal probability of a feature is above 0.25. So if you have the marginal posterior importance of a feature above 0.25, then we consider this feature to be found, right? Okay. And this is a standard like experimental design for the statistical studies in a way. So the linear features were recovered then in 100% of the time. 2-way interactions were recovered like almost 100% of the time. Even 3-way interactions for both of the algorithms were recovered always. The 4-way interactions become a little bit more sophisticated. Like for the genetically modified MCMC, only 99% of the time they were recovered, and for the second 4-way interaction it was 98% of the time. For the reversible algorithm it was 92 and 89% correspondingly, with the overall power of recovering the data generated model of 99.6 and 97%. The average number of false positives per run is 0.5 and 1, so we are on average only recovering 0.5 false features per run, and here only 1 false feature per run, and then the false discovery rate is around 6 and 13%. The previously developed GMJ MCMC for the logic regressions performed slightly worse, but also was used as a benchmark for this, because otherwise, I mean, there is nothing to compare the algorithm with. Because no one was doing anything similar in a way.
Now, what's the running time of this algorithm?
So here we were running that for 32 cores, on 32 cores. And for this example, one run would take 40 minutes on each of the 32 cores. So it's 40 minutes per one run, but we have performed 100 runs on each of the data sets. Yeah, of course, because otherwise we can't say that we have not just by chance done that. And of course, more than 100 simulations is not feasible, unfortunately, currently. So 100 was like a nice trade-off to see the balance of whether we can have some power.
Do you have like standard deviations?
I haven't, well, we could have reported them, but I didn't.
So you don't use prior to enforce any kind of sanity of your model. It's just like convenient thing to perform computations.
Yes, in this case, yes. The parameter prior for the betas. However, for the gamma priors, there we use a lot of logic, as I've mentioned, so that the priors for the gammas and for the models themselves are of high importance here. And then those priors are able to penalize more complex models.
What is their form?
Oh, yeah. Their form is... Oh, we don't have to go much further. Their form is here. So again, it's just the product of exponents of -2 times logarithm n gamma j complexity of a feature. So if feature is off, if gamma j is equal to 0, then we have 1, and it does not induce any penalty. Otherwise, we have this penalty.
The complexity is the number of arithmetic operations.
And the complexity is the number of operations within a feature.
Okay, it's interesting.
Okay. And here, I mean, I have to admit the complexity measure is only heuristically defined. I have not done any consistency studies of this particular complexity measure. Anyways, that was the first example. The second example, well, in the set example, again, to recover some ground physical laws from the raw data in the closed form. We have some data set of the explored exoplanets, which is not very large, around 500 observations in total. And then what we're going to do is to first recover the mass law of the relations of the planetary mass, radius, and the density from the data, a toy example in a way. And in the second case, we're going to recover the third Kepler's law. Right? So
What law?
it's the third Kepler's law, which was known in this form from Kepler and then corrected by Newton a few
100 years ago.
100 years later. However, we haven't been able to recover the Newton's form, but only the Kepler's form, with quite some power. We had different explanatory variables like types of the planets, radiuses of the planets, periods of rotations of the planets, mass of the planets, eccentricities of the orbits of the ellipses of the corresponding planets, the metallicities of the corresponding stars that correspond to those planets, right? The radiuses of the stars, the temperatures of the stars, and the planetary densities. And with no loss of generality, we denote those as x1 to x10.
What is metallicity, star metallicity?
I have no idea. Well, it has to be some proportion of some heavy metals or whatever in the
In the
star.
rays emitted from the star?
Yeah, well, but I have no idea, in fact. I mean, I'm not a physicist to an extent. In the first study, we have tried to recover with the same deep Gaussian regression model the mass law of the planetary mass with respect to all of those 10 different explanatory variables. Then we have run the algorithms on 16, 4, and 1 CPUs, and we wanted to recover this feature, right? And then we were considering the feature, or the particular feature to be recovered if its probability is about 0.55%. And one can say that for both of the algorithms, we asymptotically, when we increase the computational effort, can reach power 1 of recovering the feature and having almost zero proportions and average number of false discoveries. The power drops as the computational effort drops, as well as the false discovery rates and average number of false positives increase as we drop the computational efforts from 16 to 1 CPUs at best. But still, I mean, asymptotically, we were able to recover the law from the data. The second example is the recovery of the third Kepler's law. Here we wanted to recover this, which corresponds to the third Kepler's law in the Kepler's notation. However, interestingly, we have also recovered the features of this form, where instead of the solar masses, the solar radiuses and the solar temperatures were used. Interestingly, marginally, the correlations between the solar mass, radius, and temperatures is around 0.6%, something. But together with the period of rotation squared and to the power 1/3, the correlation of these three features pairwisely is about 0.999999.
Wow.
So interestingly, this is itself an interesting discovery.
Yeah.
Whether the third Kepler's law could have been dependent on the temperature, for example, but not the mass. Who knows? This is a question for the physicists. However, here we have considered all of the three.
And you know, we're still not aware about the nature of gravity. So it could be that maybe this is the initial reason.
So that's
for
the idea, so that we want to recover the laws, right? Anyways, we considered all of the three recoveries as the true positives. And if the probability, the posterior marginal probability of this feature was about 0.25%, we will count that as a discovery. In order to be able to reach the overall power of 1, we had to increase the computational efforts for this example for 64 CPUs used in parallel. Then the false positive average number is 0.02 per round, so we almost never discovered anything rather than the true physical law. The false discovery rate is around 1% in most of the cases. And in 81% of the cases, we exactly recovered the third Kepler's law in these four, which is also quite okay. As we decrease the computational efforts, of course, the power drops dramatically, and the false positives increase like up to false discovery proportion of 82% almost with just one round for the same number of iterations. But this is not the most important thing. The next slide is going to be very important for you guys because it gives you like a bit of the comparison with what would have been achieved with standard neural networks. If we now restrict our deep Bayesian regression model space to only having one non-linearity of the form of sigmoid and also allowing for the crossover operations, then we start in scenario 1 recovering some polynomials which are approximating this third Kepler's law in some form. So we have 99% of the time recover this X3 feature, and then some products of the features, but still, I mean, it's not really easy to interpret what we have found there. Though if we go further and now do not allow any of the crossovers, so the probability of crossover becomes 0. So we're not allowing any products. And then we're allowing the maximum depth of the feature to be 300. Then we suddenly start to recover some neural networks as features. Right, so like this is some feature corresponding to the neural network of depth 2. This is some features corresponding to the neural networks of depth 1 and some linear features. Interestingly, we are not going any deeper because we still have the penalty for the complexities, which does not allow you to generate more complex neural networks. But what would have happened if we had removed that penalty? So we now make all of the models and all of the features equiprobable. So we have a uniform prior across all of the features and across all of the models, disregarding their complexity. Then we start suddenly to recover quite often very complex neural networks of this order.
Quite deep neural networks.
It's not yet deep, but we have 300 other discoveries, so in each of the runs we have pretty much something of this sort. And this is indeed a deep feature, which, I mean, I can't even see how many layers it has, and I can't even interpret what it means, in fact. But this is a single feature from here to here, and then another feature from here to here, a third feature from here to.
But what is the probability of this feature?
This is about 0.25%. In case we are not using any penalization for the complexities.
So you need to perform sparse regression on the parts, sparsify this network.
Or make more flexible model space. The point is that, I mean, here we still can use the universal approximation theorem. And in fact, these features are still approximating the third Kepler's law. But now we have a philosophical and epistatic problem of whether these deep and dense approximation of the third-Kepler's law is worse or better than the one created by Kepler, because still the one that Kepler has created is a model and does not necessarily is not necessarily going to represent the ground truth. So this is just a representation of the epistemic knowledge of a human being, whether this is a representation of the epistemic knowledge of the machine.
We should apply Occam's razor in order to select the best model.
But
Yeah, sure.
Is there a date? Like that you measure something, compare error?
So, can
No.
we use like this?
No, I don't know, like
at
maybe.
the same time. In the first case,
There is
can
data
we use
There is data.
like neural networks?
Like test that?
Yeah, they were allowed in this case, but they were not
So
having.
products are better.
Yes, in this case they were better. They were having higher posterior
I mean, there are a
probability.
lot of papers about like multiplicative neural networks,
Okay.
something like this. So
It might be given some indications to something. I'm not sure yet. I mean, this is just a small example. But
What's going on if you increase the size of the training set? It seems that if you have not just 500 points, but more, this complex feature will not survive.
might be the case. Might be the case that for
You try splitting your data set in train and test, and then evaluating the test.
and not in this example, but I'm going to address in the next examples where I'm using them for predictions. Because for this example, we wanted to have the recovery of the truth in a way. So it's not used for the predictions.
Yeah, and there are some very large coefficients in this network, like
Yeah.
10 or 9.
Yeah.
Maybe there's more to test.
And this is something like gradients vanishing or something, I guess. So it would pretty much, I guess, correspond to having this feature as just one constant, more or less, I guess. And it is. Oh no, we have also, no, I'm not sure, because we have this constant level large order here, and then this coefficient with respect to this inner feature here. So I'm not really
positive.
but here, this is a negative.
Yeah, that's not
so
very
it's something
unstable.
strange.
I'm not sure what's happening there.
Don't you hit the numerical issues with computing those? Like,
What
can you actually compute that?
What weight pairs have you used? Split weights? Good Jeffrey's small uniform pairs?
This was Jeffrey's prior, but only for the outer layers.
So for the inner
For the
weights,
inner layers?
there is no prior.
There is no prior. Or uniform prior, or if you want to.
Improper uniform.
Yeah, improper uniform prior. And this is like what in here. And that's why perhaps we are facing some of those issues. Anyways, this is something that's messy and still represents the same Kepler's third law. Now we're going to use some predictions-based example where we are going to both use train and test sets to see whether the algorithm can be generalized for the predictions well enough. And the first data set is going to be some narrow object classification from NASA's Space Challenge 2016, where the challenge was to classify the asteroids of whether they are potentially hazardous objects now or not. 4Ka class, whatever, had different 8 describing explanatory variables, like mean anomaly of the asteroid, inclination, arguments of variation, whatever this means, longitudes of the ascending nodes, semi-major axes, eccentricities of the ellipses of their orbits, mean motions of the asteroids, some magnitude which corresponds to some brightness of the asteroids. And here we'll be using the Bernoulli deep Bayesian regression model. So the observations come from the Bernoulli probability distribution, which doesn't have any dispersion parameter. Again, for this example, we don't have any latent Gaussian variables. So the observations are independent and identically conditionally distributed with Bernoulli probability distribution. We have the sigmoid link between the success probability and the predictor. Here we were using the model for predictions, and hence instead of using log n, we simply have 2 as the weights, which is the archaic type penalty, which is optimal for in terms of the leave out one cross validation, at least in the linear models. It is proven to be optimal in terms of leave out one cross validation for the linear models. So if you select the model with respect to archaic model selection criteria. Again, the Jeffrey's improper prior for the betas in order to be able to use Laplace approximations. They allowed non-linear modifications where cosinus, sinus, sigmoid, hyperbolic tangents, attangents, and ARF. In this example, again randomly chosen. Okay, now some results. The MCMC algorithm here was run for just one CPU and one thread. The training set was consistent of 64 different objects, suited to positive dangerous asteroids and suited to not dangerous asteroids. The test set is 20,720 models.
Isn't it a mistake? Like the
No.
size is accurate?
No, it's not a mistake. It was on purpose selected, and even not by me, by some, I guess, Wake Up Now team, which participated in that challenge, and from which GitHub webpage have obtained the data. And they have selected these training and test sets. Then we have run several algorithms on 100 different seeds to be able to evaluate the power of the algorithms, the false discovery, false negative proportions, and false positive proportions. And then the predictions for the deep Bayesian Bernoulli regression was based upon model averaging. So we were model averaging the posterior probability of y to be equal to 1 across all of the explored models, and then making an indicator that is above 0.5 threshold in this case. Right? We have addressed several statistical and machine learning approaches, which are quite popular and have been tuned initially slightly from some random sample of the whole data set at size 100. And then the algorithm will include not only MCMC and MCMC in this case, but also lasso reach regressions, linear-based and tree-based boosting, simple MCMC algorithm dealing only with the linear models, the various deep neural networks, random forest, and logistic regression. So in this example, I mean, I'm not claiming the algorithm is uniformly better, but in this example, the GMJ and MCMC on average obtained a power of 0.99%, with some variance, of course, across the runs, and quite okay values for the false negative and false positive proportions. Lasso and Reach performed quite well. You can clearly see that deep neural networks exhibit quite some variance, having very well results in some of the runs and quite bad results in the other runs. This might have corresponded to that they got stuck in some local extrema in some of the runs.
Well, it's not a good idea to run deep neural networks on a training set
Exactly.
of 64 objects.
Otherwise, they can just overfit it for some of the runs. But in some of the cases, they were able to capture some structures of importance.
Can you run your method in the reverse regime, like with a big training set and small test set, measure accuracy?
Depending on how large the training set is.
Oh, like that like the 20K.
That could have been used. Not sure. I mean, I haven't done that, but this could have easily been used. Then I would guess that deep neural networks would perform very well too.
And your method will work?
It will work still, I guess. I haven't done that. We can give it a try. Anyways, most likely deep neural networks have overfitted in most of the runs, or some of the runs, reducing the power and increasing the false negative, false positive proportions. Again, the linear models interestingly performed quite well. There's lasso and reach regressions. Anyways, this was one of the examples. Now we have the second classification example, which is a breast cancer classification. Again, around 500 or 600 whatever observations of cancerous and not tissues. Different features is describing properties of these tissues, like radiuses of the corresponding tissues, textures, perimeters, areas, smoothness, compactness, concavity of the tissues from the computer tomography images. I mean, concave points from the tissues, symmetry of the tissues, fractional dimensions of the features, and so on and so forth. Again, the deep Bernoulli regression is addressed with the same parameters, but the allowed nonlinear modifications were chosen to be sigmoids. The indicator of whether x is greater than 1, ReLU, x to the 1/3, x to the 1/5. Training set 142, test set 427. Same idea, the same set of the algorithms. Basically, when we were using MCMC for just one thread, which is not optimal as we have seen in the yep.
By one thread, you mean the...
One CPU. One CPU.
Yeah, I understand that, but is it the number of evaluations? What is it limited by time? Because
Yeah, that's okay, yes. So in each of the threads for all of the experiments, we would run the algorithm for 10,000 iterations for each of the populations, and we would allow 15 populations.
yeah, and when you compare it to neural networks, how many epochs does it go?
So in terms of the let's say in terms of the computational time, here, I mean, even for this example, this algorithm is the most heavy. The second most heavy is going to be the deep neural networks. The third most heavy is going to be the tree-based boosting. So in terms of the time, it would correspond to having like 20 seconds per MCMC. The training set is quite small. And then like perhaps 10 seconds for the deep neural networks, and then 5 seconds for the boosting, and per one run, and even less for the lasso and reach regressions. So it is heavy computationally, indeed. Here, however, deep neural networks performed much better. They're not having such a large variance of the power of the predictions, perhaps because we have increased the training sets. The reach regression performs best. MCMC performs reasonably well, but still we can see that there is a lot of variance in these precision or power. The question is whether then, if we are using more than one thread, we can increase the power so that we are not getting stuck in some local extrema, which is clearly the case here. And in some of the cases, we have quite low power compared to the best case scenario. And we have additionally run GMJ and our MCMC algorithm on 64 CPUs. This is not fair to compare with the other algorithm because here we have used much more computational efforts. But then on average the power was increased to 0.97% and having extremely small variance in the precision. So we didn't have this issue of getting stuck in the local extrema to some extent. We have also studied different thresholds for the classification probability of 1 and 0. Not only 0.5 here, but going through different thresholds from essentially 0.1 to 1. Whatever. Finally, we have much talked about the latent Gaussian variables, but we haven't had any examples with the latent Gaussian variables yet. And here we're going to use an example with the latent Gaussian variables. And this is an epigenetic data study. We have the epigenetics data, which corresponds to the number of reads and methylated reads per location along the genome. So say that we have some genome which has some different base pairs like cytosine or whatever, C, G, and other reads along the genome. And for every location along the genome, we have the number of total reads and the number of methylated reads. So we have some binomial observations on the methylation patterns. And these are heavily autocorrelated in the space terms. Right? So these would correspond to the number of methylated reads and the total number of reads. So this is how the data looks like for the epigenetic data.
What are methylated reads?
Again, not good in chemistry and biology, whatever. This is the data set provided by the collaborative biologists, but for each location along the genome, they have different tissues, like tissues taken from a leg, from an arm, from an eye, whatever, not sure. And then they're sampling whether this particular sample taken from this tissue is methylated or not for this particular location in the genome, right? And then the proportion of the methylated ones is here, and then the total number of reads is here. So we have the binomial sort of the data, and the point is that there is strong autocorrelation patterns in this data. And we would like to not then use the conditionally independent observations, because then we're not going to be able to use proper inference. So here we have addressed the Poisson regression model with the mean parameter mu I, and the exponential link function to the predictor. Again, we are interested now in recovering the true signal and recovering the true importance features which influence the methylation patterns. hence we are using the log n penalty corresponding to the BIC or Schwarz type. Now we are not any longer using the Jeffreys prior for the betas. Instead, we are using the multivariate normal prior for the betas. And this is because in this case we are going to use integrated nested Laplace approximations for the marginal likelihood, and then it is optimal to use the Gaussian priors to be able to perform those approximations. We have allowed here 4 different latent Gaussian variables, including autoregressive process of order 1, random walk process of order 1, Holstein-Udenberg process, and independent Gaussian process.
Independent Gaussian, does it mean white noise process?
Yeah. Which is just...
So these are latent variables, these are deltas, right?
Yes. And then they would have in turn 2 parameters of the covariance matrix, 1 parameter, 2 parameters, and 1 parameter. The input variables include different features, in particular whether particular X or location in the genome is in this signature, and this genetic signature, where this is the location and these are the neighboring 2 locations. These are defined by the collaborating biologists again. Where the distance from the previous Z-design base pair is in DNA is 1, 2, 3, 4, 5 from 6 to 20 from and larger than 20. Whether the gene belongs to some class of genes of interest, there were 3 or 4 classes of genes of interest, I guess. And whether the expression level of the corresponding gene is greater than 3,000 or 10,000. And finally, we have the last covariate, which is the offset for the total number of bases for this post-law distribution. The allowed nonlinear modifications were cosine, sigmoid, hyperbolic changes, and arcadians. Just 4. Okay. Here, interestingly, after the inference and recovering the posterior probabilities of all the features explored on 16 CPUs and the threshold for the discovery probability of 0.25%, we have obtained the 4 features of interest. So the high posterior importance of almost 1 was for the random walk process. So there is definitely some correlation pattern corresponding to the unit root process or random walk process. The offset was of high importance, and just 2 linear features, whether the location is in the CG or CHG signature, were important. No non-linearities were found, which is also okay. I mean, this is a discovery, so the data did not force the non-linear features for this example. Or the penalties for the non-linearities were too heavy. Or the sample size of 500 observations is not enough to allow to have non-linearities in this data set. This is still an open question, but I mean, we didn't have any
options, too many free hyperparameters.
Yeah, that's true. That's true. But yeah. So finally, some importance of using missing data and making predictions with missing data. Assume that we have trained the model on the full data set, and then we started making a prediction for some observation, where we have missing data in this, and this model. And this is just a multi-dimensional scaled projection of the model space on the 2-dimensional space. So all of the dots correspond to different models, and this radiuses around those dots correspond to the approximations of the posterior probabilities of those models. So this is some multi-model model space with some more important models here, some of the few models here, and then the distances are based in this multi-dimensional scaling technique on the distances between the binary vectors. And this is a toy illustration. And assume that we have missing data in some of those models. And in order to make a prediction, we are just deleting from a particular prediction the models with missing data from the set V, normalize probabilities, and make predictions only on those models that are based on the full data. We don't have any missing data. And then we can handle the missing data in prediction in this way, in using all the combinations of the explanatory variables and the features for the models where no missing data is present. That was pretty much the last slides of importance. So to conclude, we have introduced the deep Bayesian regression model class and suggested genetically modified and MCMC and reversible genetically modified and MCMC algorithms for evaluating posterior probabilities within those classes. We are allowing for getting those posterior probabilities for the features and models and getting Bayesian model averaging of the predictions. The package is available in R on GitHub. So finally, what we are going, or what would be interesting to do in future. So the first important thing is to allow subsampling techniques within calculation of the marginal likelihood to be able to adapt the approach to the really big data issue. The second thing is to not use this very greedy level-wise optimization, but rather do that across all of the layers jointly. And the third thing is to calculate marginal likelihood, again, across all of the layers efficiently. So this is something to be done in future, but for today, that's it. Do not hesitate to ask questions or give comments if you have some.
I have one question. In all your prediction data,
Yeah.
why haven't you taken something when you need both prediction quality and interpretable features, like bank scoring or something? Because all your data was just, we're making predictions and we're not interested in particular decision rule, how it looks like.
Well, we could have, because I mean, it's just something that I didn't look into, but most likely here, I mean, when evaluating the results here, I mean, we were able to find out some features. I was just not looking into that because I separated the inference-based examples when we were trying to find the patterns and explain what those patterns means, like the third Kepler's law, and these were just the fully prediction-driven examples. But it would be interesting to see whether the model can be simultaneously good at prediction and inference.
But this is the main reason for this model. Because here you have a ridge regression which works the same way as this heavy model. So
Yeah.
no reason to use this model for this data set.
But clearly, if we were to use the same prediction-driven example for the third Kepler's law, since we have recovered the third Kepler's law, I would assume that the most precise predictions would be obtained by our model, right? Here.
Yes. So you need something when you need
Perhaps that is
interpretable
something
features
to
find.
include in the paper. So the paper is not yet published, it's
Okay.
written. I want to upload it to the archive as soon as possible, but my supervisor wants to make it a bit better still. But perhaps this is something that we could include into the paper also.
The problem is that the more and more superpositions you have, the less and less interpretable the features become.
We are able to tune our regularizers with
Yeah.
the.
So for example, we may overpenalize the depth, the degree of superpositions, right?
And the number of
we could
features which we
encourage,
can use.
we could encourage the larger number of small superpositions rather than small number of
Large
deeper
superpositions,
superpositions.
exactly.
Right.
That's why now I'm uniformly penalizing both the depth and the width, because the plus and the non-linearity have the same contribution to the
But
complexity.
maybe this is not the
Not
the best
necessarily.
choice
This
for the
is. Yeah,
interpretability.
I agree. Totally agree.
I have two questions.
Yep, sure.
So first question is, have you tried to do your method, have you thought about using your method on top of efficient blocks such as convolutions, say like to do architecture search with that?
By the way.
So if you have your blocks, like you are doing your thing on top of certain blocks. If you add those blocks, you use say like primitives in efficient library, like say cuDNN, and like you can do architecture search in terms of with that.
I haven't done that.
The greedy procedure of finding weights is limiting deep architecture speculation.
Can you fine tune somewhere, like in the middle?
Not yet, but in a sense, I mean, we definitely could have used the output of the most popular like architectures as input features for our model as access, and then find the configuration which is optimal. Otherwise, it still searches for all of the convolutional architectures. I mean, they become particular cases.
Okay, so like here we come to a second question. Like, how long will this method run on in this data set?
NIST, I have actually tried. There are two problems currently. I don't have the multinomial implementation.
Okay, let's do some regression.
So I can do the two Bernoullis between whether it's one or something else.
Okay.
And I can do this marginally for all of the digits, of course. And well, I was running that, but it took around 40 minutes for training on that, but the precision was not as good as I would like to report. Like
So that's full NIST.
no, I was using the sample from the full NIST for training, like
How big?
10,000 observations. But I mean, the point is that I really want to first implement the multinomial observation as the for being able to include in more than 2 classes.
But like at least are you matching like the complexity of 1 versus all linear SVM on NIST?
I haven't checked that out. So I haven't used the same benchmark data sets. I have tried to use that. I wasn't particularly satisfied, and then I didn't have time to implement the multinomial observations. This is something again to be done. By the way, this is an important thing to be done within this algorithm, because currently we have for Poisson, Bernoulli, binomial, normal, gamma observations, which are possible, but nothing else are allowed. So we don't allow for multinomial observations yet, which would correspond to n classes. This is something that I didn't implement. So.
It's interesting because recently 6 large results in neural architecture search were reported using genetic algorithms.
Okay.
Yeah, they say it's better than RL.
Yes, it
Oh,
seems
that's that.
like a reasonable approach.
It depends on its scalability.
But you can do this using MapReduce because all like you only need to do crossovers on like using a reduce operation, and all the other things can be done independently.
Seems fair. Yeah.
This I don't know of, but what I have read about is that there is this Google Brain team, which is a separate team from DeepMind, which is now using 2 neural networks, where they use reinforcement learning to train one of the neural networks to predict configurations for the neural networks. And they have also achieved quite some significant results in sparsification in terms of the having much smaller models, which can induce the same sort of generalization errors, at least as they report on their blog.
Using 700 GPUs.
Perhaps. Yeah.
Should we go to the 31st slide?
Yes.
As far as I understand, coefficients were samples, and can we look at the source column stem quickness?
Yeah.
How could we get all these coefficients simultaneously exactly like that 10 times?
Yeah, so this is because of this greedy optimization procedure that is obtained. So every feature is just obtained from as the argmax of this product, greedily for each layer, which is a convex optimization problem. Maximizing likelihood for the proper link function in GLM is a convex optimization problem, which has a unique global extrema, and we do this layer wisely.
Okay.
Yeah. And this is one of the motivations to use this greedy technique for optimization. Apart from that, it also allows you to use non-differentiable activations in a way. So you can use reduce when approximating this currently, which is not necessarily going to be easy if we allow to optimize across all of the layers. This is something to address again in the future. But this is a good question. Again, coming back to the limitations that we have induced here.
Okay, any more questions? If not, then let us thank the speaker.